I dial up to my mom's university and I download MIRC. I go onto Internet Relay Chat IRC.
That means that the file was removed from the installer file of the app itself. It was no longer there.
The advisory council she set up, it says so.
But thankfully, Xiaomi also has shitty programmers.
More formal. We're delivering
because they forgot to remove the file from the device if it was already there. So in theory, assuming that we show up to phone to own and we're one of the first few people to act for phone, and like I said earlier, ZDI usually factory resets the target device per competition. They usually have multiple devices. So as long as we could hack one of the initial devices before they factory reset it again, it's a dice roll.
So hey everybody, my name's Jen.
We still follow through. We still decide, okay, this is not that big a deal.
2021
Let's
was
fucking do this.
COVID year.
So we fly out to Canada.
It's going to be grounded for the rest of my life. I pull all the wires out of the computer. I wait for the computer to heal, about half an hour. I plug the wires back in, and it comes up.
It was my second time.
As it's coming up, everything is okay. And while the adrenaline's still rushing through my veins, I think, that is the coolest thing ever. How do I do that? And I find this, WinNuke 95. So a single out-of-band packet will crash Windows 95. And this was super cool. I downloaded this program, and now I'm an elite hacksaw. And then Microsoft released Windows Service Pack 2, which resolved this. And all of a sudden, my magical tool didn't work anymore. So how do I learn how to create WinNuke 96? And that's when I found Frack. And Frack is a magazine that's still going today. I believe it started in '85. And I read Smashing the Stack for Fun and Profit. And this just blew my mind. The simplest C program that says, hey, what is your name? You have allocate 100 bytes and you type in your name. And if it doesn't check, and it just prints, hey, hello, your name. If you type over that 100 bytes and you're not checking for 100 bytes, you can start overwriting memory, and then you can overwrite a stack pointer, and then you can point back to the beginning of your name, and that can be shellcode, and that can execute code on the computer, and you can take over a computer with an extremely simple program. And that taught me that the way a system works is not how we think it works. Like, I want to now understand what is the ground truth. But how do systems actually work? How does a computer actually work? It's only when you understand the CPU architecture and memory and how, when you're compiling your C code and assembling it and linking it, how you can actually take over the system. And over time, as I've learned from many of you and from papers and from videos and just testing things, that ultimately everything boils down to energy. Like, everything is energy. Information is energy. By energy, we're talking power. Energy is the capacity to do work, so to perform some type of work. Power is the rate at which that work is done. So, for example, a horsepower. Like, a horsepower is actually a unit of power. 1 horsepower lifts 550 pounds in 1 second by 1 foot. I looked it up on Wikipedia. It's actually imperial horsepower. That means there's also a metric horsepower, which lifts 542 pounds, slightly less. I'm not sure what we're feeding our horses. Probably HGH, horse growth hormone. So energy in power, and I realized energy is information. So if we want to actually move any information around, we must use energy. An example of that is, we think that there's power in data, but that's not true. Power is data, and data is power. If you have a USB 2.0, you plug your USB in, it doesn't work, so you plug it up the other way, it doesn't work. The third time it always works. When you plug that in, there are 4 pins. There's ground, power, and then data, differential data. Now, the ground and power, there's energy moving over that. But there's also information across that. If you're plugged into a computer that's encrypting something, there's going to be some information of that encryption about the amount of power that's being, and that's going to ride on the power. Like, the power rail will actually go up and down just a little bit. That 5 volts will move up and down. You can measure that. And then there's the data. Well, how does the data work? Like, what is actually going across the data lines? That's voltage. So there's actually current in voltage, which is power, pushing through those data lines. So you can always extract power from this stuff. And I remember I'm sitting at my computer maybe 15 years ago, and I had these Dell speakers on my computer. And I got a text message, or I was about to get a text message, and I don't know if many of you recall that sometimes you get this interference. You get a text message or a phone call, and then your speakers would go do-do-do-do-do-do-do-do-do. And I was like, wait, my phone's not connected to anything. Yet the speakers are actually playing sound. Like, there is some sort of interference here. how can I control that? Like, if my phone can do that, so it's not actually the cell towers, it's actually your phone trying to amplify the signal and get back to the cell tower. The cell tower is far away, so it
Except
amplifies
that's
the
not the
signal.
end of the story.
And I thought, okay, well, can I open a keyboard? Can I look at how the keyboard works? And if my phone can interfere with the speaker, can my phone then interfere with the keyboard? And can I press keystrokes? So I opened up a keyboard, and it's a USB keyboard. And when you open it up, you have a circuit board that's PCB, your fiberglass, and then you have all these conductors. And every conductor, going to every key, is a unique length. And they're all copper, they're all metal. Any piece of metal is an antenna. If you measure that antenna, the length of that antenna, that's a monopole antenna. That measurement is the wavelength, the resonant frequency. So you can figure out the resonant frequency of every wire going into that. And I thought, well, can I create an electromagnetic radio that can then inject keystrokes into this keyboard wirelessly? And I started to try to do this. And I started to realize that it's not working. I tried a couple different software-defined radios like HackRF and the USRP B210, and I was never able to inject all the keystrokes I wanted. With one keyboard, I was able to inject a few keystrokes. And I'm like, I really just don't understand electromagnetism enough. So I started to learn about physics. And I started to learn about, well, what is electromagnetism? It's really light, light and radio. And took a picture of a rainbow on a jog. And really, electromagnetism is light. We can split that light up into its constituent wavelengths, and there's all sorts of other frequencies. So radio, for example, is light. Radio is just colors of light that we can't see with our eyes. And as I wanted to learn about this and how this stuff works, I started learning about light and EM and radio, and I need to learn physics. So I started to get some physics books and start reading about this stuff. One of those books was Building Scientific Apparatus. And I learned, okay, well, a lot of the people who were learning physics, which is really how hardware works and how radio works, they started by like J.J. Thomson, who broke the atom open. Like, it's called the atom from Greek atomos, meaning indivisible. Until this dude, J.J. Thomson, put a bunch of atoms inside of a glass tube, evacuated, pulled almost everything out, put high voltage, and then it split the atom. It was divisible. And then he used magnets, and he could move the atoms that were producing light. And that became our cathode ray to our CRT TVs and monitors that we used. I'm like, this is super cool. I should reproduce this. So I set up a little glass blowing station at home, and I tried to blow glass and do some lamp work, but all my stuff would always break. Like, I'd make something and then it would crack. I'm like, all right, I need to actually learn some glass blowing. I took some classes in LA, but these are all soft glass, and I still would come home and I'd try to make some stuff that would break. Then I went on the internet and I found this guy who makes all sorts of borosilicate glass, which is like scientific glass blowing. And I messaged him, and I messaged every other scientific glass blower in Los Angeles. Hey, I want you to learn how to glass blow. I will pay you. Everyone said no. Like, I have a job. You can't just come to my work. And that's probably like illegal or something. So I went on LinkedIn and I searched more scientific glass blowers across the US, and I just messaged everyone. Like, someone has to say yes, right? Someone will like let me pay them for a few hours, so I can just. And I get a response from Katie. Hey, I see that you're in LA. We're in Milwaukee, Wisconsin. Is this something that you would travel for? So a week later, I get, Delta tickets are very cheap to Wisconsin in winter. It's because it's freezing in Wisconsin in the winter. It's so cold. I show up to this place, and I say, is Katie here? And an old woman answers the door and says, there's no one here by that name. I'm like, what? Did I just get pwned by someone that I reached out to? Because I put a deposit, I flew from Los Angeles to Wisconsin, and I'm just standing. I'm cold, I'm uncomfortable, and the person that I paid is not here. I look at my email, we never called each other, we just like chatted on LinkedIn. And then I found her phone number, I call her, and she says, oh, I'm sorry, I switched the numbers. Fortunately, she was down the street, I walk down the street, we go into Ian's glass blowing station. So Ian and Katie are these two scientific glass blowers that work for a big science company in Wisconsin. And I go into their shop, they show me their glass blowing lathe, their fume hood. Here's Ian showing me a lighter that he made, Katie with her lightsaber, that's fire. If you ever want to learn how to glass blow and you're in Wisconsin, you can email them, contact them. And I came back learning a little bit more about how to actually, you wanted to pick? Yeah. I came back home able to actually blow a little bit more borosilicate glass, which is great. And when I came home, I was very excited, and I started to reproduce some of these. I made a little cathode ray tube, and I started to learn more about physics and more about waves. And one of the biggest realizations, one of the most helpful realizations for me is that it's very difficult for me to understand complex things. I don't understand complex things. I can only understand simple things. But I can take simple things and build a simple thing into a module, a block, and then use that block with another simple block, and then build stuff on top of that, right? And if I can find patterns, then that makes my life much easier. I don't have to learn X, Y, and Z. I can just learn an abstract concept of what X, Y, and Z are if they're the same. And we can interpret everything as waves, as analog signals. So a wave has three things that are important. Now, when I say waves, light is a wave. Sound is a wave. Water waves are waves. They all have the same properties. They have absorption, where they absorb and convert from one type of energy to another energy. They have reflection. They have refraction and diffraction. Intensity. So the sound would be how loud it is. That's the amplitude. With light, that's how bright it is. Then there's the wavelength, which directly relates to frequency. So a low frequency light would be red light. A high frequency light would be blue light or UV light. With sound, the low frequency is bass. High frequency is higher frequency sounds. And there's phase, which is where something is in its amplitude, because amplitude is moving up and down. And when we're dealing with computers, we're digitizing things, we're quantizing, which just means our microphone, when I'm recording my Metallica CDs, or I'm backing up my Metallica audio, of course, I go into my microphone, let's say, and that has a sample rate. And the sample rate is the number of times per second I record. Or a frame rate. When you're taking a video, then if it's 30 frames per second, that's a sample rate, 30 hertz, 30 times per second. And the bit rate, that's the depth. So that's how much quality or resolution we have. And these are really important factors. Also, waves can do very interesting things like interference. So with interference, we can do constructive and destructive interference. So your sound canceling headphones, when you put those on, they have microphones on the outside. So that when you're listening to the Metallica that you ripped, backed up, you hear the outside sound, and the microphone takes that outside sound and it inverts the wave. And then it plays it along with Metallica. And those two cancel out. Just like a water wave with a high peak, high amplitude, and a low amplitude, if they hit, they will cancel out. So that's destructive interference. And there's many other places online and on the internet where you can get free tools to learn about physics, such as Veritasium's channel. So Veritasium has amazing videos on physics. And there's so many interesting attacks that we can do with light. Here's Newton actually designing the cover for Pink Floyd's album, Dark Side of the Moon. I always thought that it was white light going to the prism and then refracting into the rainbow, but we're reverse engineers, so how do we know it's the white light going in versus the rainbow going to the prism and converting to white light? We don't really know. That's an interesting property of physics, is that physics, almost everything works in reverse as well. If you have a speaker, then you're playing sound through that speaker. You have voltage going into the speaker, and that's electrons moving through a coil. And any moving particle, every moving charged particle has a magnetic field. And that magnetic field is pushing the speaker cone back and forth. That speaker cone is then pushing air back and forth. And that's what the sound is. The sound is the movement of matter. And the reverse is true as well. So if you have a speaker, and you have air moving the speaker cone because the speaker's not on, then the speaker is also pushing electrons back and forth, which then produces a voltage in the coil. So every speaker is a microphone. Every microphone is also a speaker. Now, they're really poor quality versions, but it's true. And this is true with LEDs, for example. Every LED can shine light, but if you monitor the LED, you can actually have the light convert to voltage, and you can read light from an LED. Everything works in reverse. It's an important property. And these are ways that we can take advantage of energy and energy conversion, and the way that things actually work at a fundamental level. Here is a little bit of the electromagnetic spectrum. We can see the different colors, but it's also important to note that, again, things like UV and IR, those are light. Radio is also just another type of light. It's just light we can't see. It's colors we can't see. FM radio is frequency modulation. So when you tune into 102.7 KISS FM, you're listening to 102.7 megahertz on the electromagnetic spectrum. 102.7 megahertz. And now the frequency is modulating. All that means is when there's audio, if you have a 10 kilohertz tone, it's a high-pitched tone, that's 102.71. So 102.7 megahertz plus 10 kilohertz. So your frequency is actually just moving up and down at 10 kilohertz. So you can think of an audio wave going like this. If we just flip it 90 degrees, then it's actually going like this, the frequency of the spectrum. Amplitude modulation, AM radio, when you listen to 98.7 AM, that's 98.7 kilohertz in the electromagnetic spectrum. And the amplitude is going up and down to the sound. Now you can do some really cool things with light. There's the light commands research that people did, where they found that if they shine a laser at something like Google Home, they can say, "Hey Google" with light. They just modulate the light. They turn it on and off. Where modulation just means turning on and off or oscillating. They turn it on and off to the frequency of sound. And if they record their sound, "Hey Google, unlock my door," and they turn that light hitting the microphone is heating up. It's absorbing inside of the microphone, the MEMS microphone, and that produces heat. And heat is vibration of particles. And that microphone then believes that it's hearing sound. So that means you can shine light through a window and trigger the Google Home to do things for you. There's also infrared lights. This is Mark Rover did a video showing just a thermal camera where he then pressed a pin and heat is constantly transferring. So just by touching these buttons, heat from his finger goes to the button and then leaves a mark. We don't see it with our eyes, but with a thermal camera, like a FLIR camera, you can do that. Ultraviolet, so ultra, from Latin meaning beyond, on the far side of, so it's on the far side of the visible spectrum. Bunny did an amazing example with ultraviolet light, where he took a PIC microcontroller that had firmware that he wanted to extract. But the PIC microcontroller had an E-fuse, an electronic fuse that said, "Do not allow anyone to debug and access memory from this." And he opened it up, he used nitric acid, sulfuric acid, to get to the silicon. He covered up the area other than the electronic fuses, and then he shined UV light, which erased it. That's how programmable read-only memory used to work. We would shine UV light to erase it, and then we could program it. Then there's radio, which again is just another part of the spectrum. We talked about FM a little bit, we talked about AM. We're all familiar with, say, 2.4 gigahertz Wi-Fi or Bluetooth, 5 gigahertz Wi-Fi. Our microwaves, the microwave that you make popcorn at home, that's actually 2.4 gigahertz. Microwaves and radio are the same exact thing. There's the Tempest attack. The NSA found in the 60s, they knew that a CRT monitor, a cathode ray tube, would constantly emit radio frequency. And that radio frequency, they could hear in an adjacent room. They could essentially listen to the radio frequency and see what's on the monitor. And there are modern attacks like this today that are happening. We talked a little bit about the AM and FM. Then electromagnetism, electro from amber, because the Greeks found that when you rub amber with something like fur, they would attract or repel. And magnetism from magnesian stone, because there's a place called Magnesia where they found stone, and the stone was attracted to other magnesian stones. We realized later it's magnetism. This was an example project a few years ago called MagSpoof. I was interested in how the mag stripes actually work within our credit cards. Oh, that's loud. And I put my credit card inside of iron oxide filings. And you can actually read the ones and zeros off of my credit card. I'm not even sure why I put the electrical tape, because you can just read the credit card number off the bits at the top. And I thought, all right, what are all these numbers? And it's a credit card number, there's a CVV. There's actually a separate CVV. There's a written one, and there's one in the mag stripe. Now, we think, all right, well, who uses mag stripes, right? We all use chip or NFC. But have you ever put your credit card in a mag stripe machine? It's like, hey, this is a chip card. Well, how does it know there's a chip card? Well, the mag stripe tells it. The mag stripe says, no, there's a chip card, you need higher security. So what happens if you turn that 1 to a 0 and say, no, there's no chip on here, there's no NFC? Well, this is the device, this is the MagSpoof device, and it just produces a magnetic field. And if you I used a chip card, I put the mag stripe data onto this, and was then able to make transactions without the chip. So if you just have access to a mag stripe temporarily, you can then convert the chip to a non-chip card. There are some other interesting attacks. There's sound. There's so many interesting things that we can do with sound. There's audible sound, which is what humans can hear. We can hear 20 to 20 kilohertz. I'm a little older. I can maybe hear to 15 kilohertz. If you listen to a lot of music, you probably hear less. Berkeley had some amazing research where they used a microphone to listen to the sound from a keyboard. And there's a lot of research that I was able to fortunately take advantage of in using other people's tools and research to learn how can I understand what's happening on a keyboard. There's something really interesting about all the information that we are constantly inputting. Maybe that's because I'm on a computer every single day typing. I think it's cool to know that what am I typing? What can someone figure out what someone else is typing? And they're able to just have a microphone, listen to what the sound your computer is making, and convert that back. 2 keys. Ultrasound, again, ultra on the far side of. The University of Tel Aviv had some awesome research where they were using a microphone from a standard cell phone, and they would listen to the ultrasound coming from your computer. As your computer is performing encryption operation, let's say it's using RSA. RSA, if you're encrypting a 1-bit versus 0-bit, it takes different operations. It might do a multiplication followed by a modulo, or an exponent followed by a modulo versus a multiplication. And because of those different operations take different amounts of power, that's different amounts of power going through capacitors and inductors of the CPU. Those capacitors and inductors are producing all of these charged particles, all these electrons moving is producing magnetism. That magnetism is then moving things on your CPU. So these actual caps are moving within your CPU, and they're producing ultrasound because they're moving at a frequency higher than we can hear, above 20 kilohertz. So if you can hear that with a microphone in a lab environment, then you can convert that back to 1s and 0s and extract secret keys. Pretty amazing stuff. All of this is really just energy conversion. Everything that's happening is a conversion of energy, and that's really interesting. So how can we take advantage of energy conversion? And I started to get interested in laser microphones. So I saw a talk 15 years ago here at DEF CON, and it was incredible. It was about how to use a laser microphone. Now, the first laser microphone, not really a laser microphone, but a microphone that was, let's say, passive, was from Leon Theremin. If you're familiar with the Theremin instrument, Leon Theremin created this Theremin instrument. He was an engineer and physicist. He also created something called the Thing, and he gave this to our friends at the KGB. And the Thing was a passive device. Many of us are familiar with RFID devices. They're passive cards, and they go into a field, an RFID field from, say, a reader, and that reader emanates radio. And then that energizes the card. The card now has enough power that it can run a little processor and respond. Once it gets back, this was the first implementation of RFID. And instead of a card with an ID, he put in a microphone. And that microphone then went into a seal. And this was a gift that the Soviet Union gave to the US ambassador in 1945. They put that, no battery, right? No battery at all. Because Leon Theremin realized that he could passively power things. He could power things from far and then get information back. It was many years before the US realized that there was a microphone. Whenever that they were being powered from the outside, they could get audio back. Now, laser microphones is a way of using light in order to listen to sound. So if I can shine a light at a window, and the window, now sound is the vibration of matter. Typically air, right? We're typically listening to air, but you can have sound go through solid materials, you can have sound go through water, liquids, and you don't actually need a laser, you just need light. And the light can be visible or invisible, as long as we have a way to receive it. So it was this talk, Sniffing Keystrokes with Lasers and Voltmeters, by Andrea Barasani and Danielle Bianco at DEF CON 17. And this really blew my mind. What they were able to do was they were able to point a red laser at a reflective part of a laptop within a room and then pick up the reflection on a photodiode or photoresistor. And they picked it up, they plugged that into their sound card, and they were able to listen to the keystrokes. Now, it took a lot of work, definitely a proof of concept, but absolutely incredible. And I've always been interested in these keyboards. A few years ago, I released a project called KeySweeper. KeySweeper is just an Arduino-based device that's inside of a USB charger. You plug the USB charger into the wall, and it's just sniffing every Microsoft Wireless keyboard in the vicinity. It also has a GSM chip, so it's actually connected to a cell phone network. It has a battery inside, so if it gets pulled out, it continues to operate. And then you can inject keystrokes, and you can listen to all keyboards in the vicinity. Fortunately, the FBI released a notice to the industry saying, watch out for these KeySweeper devices. And I read that, someone sent that to me, and I read it said, limit which outlets are available for device charging. Some suggestions just for all of us. Know which chargers are currently being used. Immediately remove unknown chargers whenever you see them. I don't think they realize that it's really just the circuitry inside the charger. The charger was just to be clandestine. So you could put it in a banana, at which point you would have to limit which bananas are available for device. You'd have to know whose bananas are currently being used and immediate removal of any unknown bananas from the office. So beware of bananas and USB chargers. But keystrokes. So these guys demonstrated the components that they used, common laser, like off-the-shelf laser, resistor, battery, and this was their schematic. So what they did was they had the laser hit a laptop, it would reflect off the laptop, and then it would go into a photodiode or a photoresistor. They would power that and they would go into the microphone. And the reason for the microphone is that that's an analog to digital converter. That can convert the actual light waves, so the photodiode converts the light waves to electricity. And that electricity is still a wave. It's just like our AC. So our AC that's producing 120 volts RMS voltage in the wall, that's traveling at 60 hertz, 60 times per second as we're moving up and down. And you can actually take advantage of that. I was curious actually whether it really was 60 hertz. So I had connected a transformer to my AC line and converted that 120 volts down to 12 volts. And then I measured the zero crossing every time it would cross zero. Because I was curious, it says 60 hertz. Does that actually mean 60 times per second? Or does it mean like between 59 and 61? And I found the 60 hertz is more accurate than the clock in my phone. So if my clock in my phone is not on Wi-Fi, I can use the 60 hertz from the wall to measure time because it's so accurate. And I didn't understand, why is the 60 hertz so accurate? Apparently it's connected to GPS. So if one power station goes down, another station can pick it up. But the interesting thing is, it's not always accurate. It would actually remain accurate only for a short period of time, and then it would drift. And I realized that you can take advantage of that drift, and you can exploit that. So what you can do is you can say, if I measure that drift over time, you can take that and use that as a fingerprint of a location, because every power station has its own unique fingerprint of that drift. So if you put a Raspberry Pi in a transformer in different power stations, just in the wall, you can have a public database where you're all sending the drift of this information, of the 60 hertz signal. And now whenever you have a recording, a video recording or an audio recording, you can perform a match and figure out where that audio recording was taken, or where that video recording was taken. Just another interesting project that we could take advantage of. And there's so much other interesting research in the laser microphone and the keyboard acoustics. Ben Nassi, he did lamp phone, glowworm, many other attacks. There's the visual microphone, there's keyboard acoustic side channels, keyboard acoustic emanations. And I wanted to see, A, can I implement this laser microphone, and B, can I have some improvements? And can I also hear sound? I want to hear sound from a window. Now first, it's really, really important. Like, lasers are not a toy. I mean, they're a lot of fun. Cats love them. They're toys of cats. But you can, you can burn your eyes. So you do actually want to always use laser safety glasses, goggles. When you're buying a 5 milliwatt laser, it doesn't mean it only outputs 5 milliwatts. It can output much more power. America, we have the ANSI standard Z136.1, Europe uses EN207. Make sure you're getting from a laser safety goggles from a reputable source. And also for the wavelength, for the color of light that you're working with. Let's talk about hardware. So I first tried to re-implement the original laser microphone, and it took me a while to get it working, and the sound quality wasn't great. Now, it was still incredible. Like, as soon as you get to hear sound that you're bouncing off a window and then reflecting back and picking up, and you can hear what's going on inside, it's a really magical feeling. And I want to see, can I improve it? Can I improve the quality? Because it wasn't that great. Here's my transmit side. So we've updated the system a little bit. The primary things, the primary differences, for one is you just have a laser and you point it at the window. Every schematic, every laser microphone I've ever seen simply has a constant laser source, hitting something and reflecting back. The problem I found with this is that there's so much noise. We have the 60 hertz from the wall. We have all sorts of noise from computers around. And all this stuff is typically low frequency noise that's messing with your signal. And we need to get rid of that. So I found a laser driver. This was a laser driver I had that had something called an RF IST. And what this means is it's a mixer. So you can have a constant current source that's powering the laser, and then you can have another source that's oscillating. And I was thinking, well, what they do in radio is that they'll oscillate things at different frequencies to get away from other frequencies that might be harming. So what if we turn the laser on and off in the RF domain? If we go into radio, and we're turning that light on and off at the radio frequencies, then we can actually get away from all that noise that we hear. Here you can see the different parts of the system. So oscilloscope in the top.
that
I use that
reverb.
simply because I have a signal generator
Reverb
built
go
in.
up or down?
So Rigel. I'll have the full details, the full bill of materials in a future slide. But the current controller and temperature controller, you do not need a temperature controller, but that's just what I have at home. Current controller for the constant current source. In the top, there's that black box. That's the laser driver. There's also the RF mixer built into that. I use a collimating lens. So what collimation means is, collimation means it just takes light and tries to make it into a single dot, or a straight, if you take a flashlight, you typically have an unfocused beam of light. A collimated beam is a beam that does not focus or defocus. I used to think a laser, what made a laser was that it was collimated, that it was a straight line, and that's not true. It's not collimation. What makes a laser is that it's coherent. And all that means is that the phase of light coming out is always the same. It always starts at the same place. It's not important for this attack. I thought that was interesting for me to understand what a laser is. The flexor, that just lets us actually direct the lights up and down very easily. A shutter is to really tighten our beam. So even though we have a collimation and we're collimating this laser beam, we want to get a really tight beam. So a shutter just lets us close that even further.
I don't even know.
And behind the lens, there's a laser diode.
Anyway, thank
and
you for
all of
coming.
these you can
Yeah,
buy
move
separately.
on.
And the nice thing is that with the laser diode, I can use a red light normally when testing, but then I can move to the infrared where we don't see it. So these are the actual components I'm using. The obligatory turn on the fog and check out the cool red laser beam. Then we want to actually receive that information. So how do we receive it? The typical setup is we have a photodiode and a sound card. But what we're doing is we're modulating. So with the signal generator, we start modulating this thing at hundreds of thousands of times per second. So that sound, humans can hear between 20 hertz and 20 kilohertz. So I want that sound. But I want to then get away from those low frequencies because there's so much electromagnetism at those frequencies that it's disrupting the signal I'm getting. Because we're getting very little light back from the laser that's reflecting off a window or off a computer. So first, and the sound card can only listen to, say, 48 kilohertz or 192 kilohertz. To get away from all that sound, we modulate the laser. We turn the laser on and off 400,000 times per second. So we're at 400 kilohertz. So we need something other than a sound card that can actually accept this. So first, I thought, okay, well, I can use a bunch of analog components. The problem with analog components, electronic circuitry, is it's a huge pain. So as you're putting these little components in the circuit board, for one, you're dealing with high frequencies. So as you're trying to change as you're trying different filters and amplifiers, all of this is very difficult. And think, man, I really wish I could use GNU Radio. GNU Radio is open source signal processing software. And with that, then I can drag and drop, and life is just great. I can sit back in my chair, drink some caffeine, and just play with these blocks, and just test different things to see what works. The problem, the challenge with using GNU Radio is that I need then a software-defined radio to pull that data in. The sound card won't work, because I need something that can listen to not only 400 kilohertz, I need to go at least double that. It's called Nyquist's theorem. I need to go to at least 800 kilohertz of a sample rate, how fast I'm listening to that data. And I can use a software-defined radio, but software-defined radios don't ever go that low. So the RTL SDR, I'm not sure where that goes, maybe 100 megahertz, excuse me. The HackRF, amazing, I love the HackRF, but the minimum frequency it can listen to is at about, 1 megahertz, and we're at 400 kilohertz. The USRP, it also has a very low bit rate, so it's about, the analog to digital converter has an 8-bit sample rate, and we want higher samples, we want higher resolution, so we can extract more signal. The USRP B210 has 12 bits, which is good, but it requires 70 megahertz, and we're just down at 400 kilohertz. But then I started looking, and there is something called an upconverter that we can get. So the upconverter actually adds 125 megahertz to a signal as long as it's at least 100 kilohertz. So we're at 400 kilohertz. So ultimately what I used was a photodiode. I go into an amplifier. That amplifier then goes into a Hammond up, V2. That adds 125 megahertz to our 400 kilohertz. So now we're at 125.4 megahertz. Then I go to the USRP. Now that can go into my computer. Here's the physical setup. This is the receiving side. Lens to capture light, into a photodiode, into the amp, into the USRP B210, into the computer. If you see this outside of your window, it is super sketchy. Maybe shut the blinds, call the police. But once you actually point this laser at a computer, Now, there are some big challenges here. Actually, performing alignment is very, very, very challenging. Getting sound is actually not so challenging because our ears, we're pretty good at listening to just 1 kilohertz of sound. Although we can hear up to 20 kilohertz, just 1 kilohertz, we can usually make out what someone is saying. Getting above, I'd say, the best I was able to get above was 4 to 5 kilohertz of sound. And I found for keystroke extraction, I needed to get to 3 kilohertz. If I got to 2.5 kilohertz, I could not convert anything to keystrokes. If I got to 3 kilohertz, I could start converting to keystrokes. Here's the hardware on the transmit side, just the actual components, just so you know. Here is the RX side. This will all be online, so if you want to know the exact components I used. And one of the other improvements that I wanted to make here, for one, now that we're getting into the RF domain, we get away from all this noise, and we can actually filter out that noise. Another cool thing is I wanted to do this in infrared. I don't want someone seeing me standing outside pointing a laser into their window. That's just too obvious. So I got an infrared laser diode, and how do I actually align to the infrared? Because I can't see it. So I got this infrared camera. It's the X-Night USB 2S M. It's around $120. It's very cool. It's actually very exciting to be able to see infrared, right? Just being around you. And it's maybe hard to tell, but I have the laser diode going and hitting a white square, and you can't see it on my camera, my phone camera, because my phone camera also can't see IR, and my eyes can't see IR. And then here's, just so we can see, I did a recording with that camera, pointing the laser at my laptop, and you can kind of see the reflection. I'm sitting below the laptop with a steam iron, and I'm just like steaming my laptop until, I think it was the first time I ever used a steam iron, until boiling water boiled down on me, and I was like, so I got maybe a few seconds before I burned myself. But while I was doing this testing, I also saw something else interesting. I pulled out my phone, and I wanted to change the song because Spotify was playing. And when I unlocked my phone, I saw these dots, not on the wall, but I saw it on the IR recording. I'm like, wait, what's happening? When I pulled out my phone, I realized this is LiDAR. So my phone is using LiDAR on the back. I'm like, why? Why is it projecting all of these infrared dots that we cannot see with our eyes? And it only happens when the camera app is open. And it's actually very cool. It's figuring out how far is the object? How far is it? And if it's close, it's going to use the close camera. You have a bunch of cameras on the back of your phone. So it's deciding which camera to use. So when you go closer to an object, it will automatically switch to a different camera. And I thought, well, that's really cool. Well, what if I can actually measure this? So I put this in my spectrometer just to see what wavelength of infrared this was. Because now we can just monitor for this wavelength of light. So imagine you have a little device with a photodiode, a photo sensor on you, so that whenever someone points their phone camera at you, you get a little vibration. Because you can just measure for that frequency of light and for that on and off path. And now you can know when someone points their phone camera at you before they're even recording. And it only will show, you can see that sort of rectangle, that's exactly the same path. That means I could just make all of you vibrate right now. How fun would that be? So, separate project, we'll do that another time. So there's the RF modulation. This is the biggest improvement that I've seen in this laser microphone. So actually getting into the RF domain. The photodiode I use, this is the Spot 2D. It's pretty interesting. It actually has 2 cells. So where photodiodes are typically 1 pixel, this is really 2 pixels. The biggest challenge of this whole system is that you must get essentially to the edge of the diode. You don't want to get the light in the center, you want to get to the edge. Because as soon as the edge, you essentially want your light, your reflection to go on and off that diode. If you're in the center, then you're not going to get much variation. But if you're at the edge, that's where you get all the variation. I noticed there was a hair in their photo. Fortunately, there was no hair in the photodiode they sent me, so I didn't have to send it back.
Well, thank you.
Software that we use. So
Wonder Twin Powers activate.
Awesome software. First, GNU Radio. And we'll quickly go through the steps here, but all of this will be online as well. So GNU Radio, all the red stuff on the left, those are just variables. That just makes it easier for me to, just like in software, to use a single variable that will change things in multiple areas.
The AI will unleash me?
Circled in blue, those are just graphical syncs, so we can see information. The heart of the GNU Radio stuff is, first we start with our USRP source.
Front of AI.
So this pulls in data at a sample rate of 4.8. megahertz or megasamples per second.
It's
Our
really,
center frequency
we might
is
have to drink to the end of
125.2
CAPTCHA.
megahertz. So 125
I mean,
megahertz.
if AI is that good, right? I mean, so for example, we run this
200 kilohertz.
You count on to the fact that we're really big in the community. And so DEF CON, a couple of years ago, we started this Mastodon server,
Any software
DEFCON.social.
defined radio is going to give you this giant DC spike, and you want to move away from that, and then you filter out that DC spike, and then you can listen to the actual data you want. We mentioned a couple different SDRs. The reason I chose the B210 was because it had a high resolution.
While speaking about methodologies, we cannot skip fuzzing because
This is a Salier logic analyzer. I realized this is also actually pretty nice. It's 50 megasamples per second. It's also 12 bits. Then we go into a translating FIR filter. This is three things. First, it's a bandpass filter.
So this particular
first, it actually changes the frequency you're at. So we want to go from 125.2 to 125.4. That's where our sound is. So now we're centered on the sound. And the sound is moving up and down. So our signal is some sort of sound wave, but our amplitude modulated signal is at 400 kilohertz. So it's going up and down. So the FIR filter will also then do a bandpass. So now we're saying, I only want what's around the 400 megahertz. Excuse me, 400 kilohertz. Everything else we can
Sammy
control.
Camcar.
So we bandpass that out, and then we decimate. Decimate just we bring the sample
Rehashing
rate
a
down
few
to a
things,
more usable sample
but
rate.
talking about
Then we go
using
into
laser bounce
amplitude
for,
demodulate.
as a microphone.
So we convert the
Oh,
AM
yeah.
to the,
That's always
the
fun.
actual sound.
And
Yeah,
So
always
now we
strap
hear
the dildo to your
sound, and then we
windows.
save the file. Then we use something called
And
isotope RX. This is
other
absolutely incredible
audible
software. It's commercial
extraction
software,
things like
but
being
it's
able to
very
determine
good.
what keys being
It's
pressed by
great
the
at
sound of the
spectral
keyboard
repair,
clicking.
and it gives you a spectrograph, so you can actually
Yeah,
see
and
what's happening inside your
getting
signal.
into a bunch of
And then you
stuff.
can do all sorts of things like
And
DS,
then,
D-hum, D-explosive.
Yeah, that kind of stuff makes me want to like start a business.
But it has a lot
And
of
then-
ways that you can then
because you know, like at like
improve
networking
you can
events,
say,
how
hey,
like
I want to learn this area of
all
sound
like
where
like
there's just a lot
VC
of
kind of
noise.
people that like
Learn
to feel
that
like
and
really
apply
smart
it
and
to the rest
important,
of the
or like
signal and
all
remove
like
that
just
noise.
chatting it up and stuff.
FFmpeg,
It would be
just
so
we
easy
can
to
actually
sell them
convert some
on
things
like a
around.
little like
And then
transmitter
keytap
that you
is
can
really
just
the
like
heart of the
stick to your
system
window
the
for this kind of
keystroke
stuff and just like
extraction. You wanna
freak
know
them
what
out
the
about like
person's
corporate
typing.
espionage and
And
shit.
I like this guy's
And then
video
get
that
them to
says,
buy
I
like a
the
system for like
BRC
$5 grand and just like
so
go and just like
keytap
stick a
3 is
little
part of this
like motor to the
software
window
where he
basically.
takes audio
That'd be pretty
and
good.
he's able to then separate out the keystrokes. Now, what's interesting is that when you have a keyboard and you press some keys on it, every key produces a unique sound. Now, we're not recording sound, we're recording vibration.
Joe's
because we're
talking
hitting the
about
laptop and reflecting
predicting
off. And when
passwords
someone's
from the
typing on that
past
laptop,
to
the
hack the
sound is
future.
just vibration. And vibration matter. So the laptop is vibrating.
Yeah, I like that
It's
heat
literally
map
vibrating.
passwords.
And because every unique key
You've seen
has
that
a
one, and
position,
there's like,
just like if
you
you
know,
hit
that
a
nice
drum,
solid
if you hit it
diagonal.
you hit it
Yeah.
in one location, you're producing one sound. If you hit it slightly somewhere else, it produces a slightly different sound. You can record that.
What's really
and you can
curious is all black
differentiate those two
pixels.
sounds. Then you can
It
figure
seemed
out
really
what
random
they
where it's just
actually
like apparently nobody
Now, on a
uses this
keyboard, you
password.
don't
It's
know
like, huh,
what they're typing. You don't actually know what
probably
they're
more
hitting.
interesting than what
But
the passwords
if
are.
you collected over 100 or 200 keystrokes, and you know the language they're typing in, then you can perform analysis and say, and frequency analysis, like what are they actually typing? This is a Zodiac killer. So he would release these puzzles that are essentially substitution ciphers. You can take all encryption and break it down into substitution cipher and transposition cipher.
Fun stuff. There's like a movie night
Just
5
an example, I love the
that
outdoors.
Jess is doing
So
for
going
her.
in, as well as pointing lasers. So a
Toastmasters
couple
Club.
demonstrations of the setup.
I'm gonna probably get ready and head
Here
over
we can
there
see
and
what this actually
help her
looks
pack.
like
She's moving tomorrow
as
into
you're
a new
pointing the
spot.
laser onto a reflective
So,
surface of a laptop. We'll just
yeah,
see
it's
the
gonna be a
keytap
big day.
software, FFmpeg and
Cool.
keytap running. This is at 10x speed.
Catch you later.
All right. Yeah, and there's game night at Dojo tomorrow
On the next
night,
slide, I will do a little
and then
screenshot
flea market
so we can
Sunday.
compare.
Oh yeah, because it's
Again,
the
that's
first one
10x
August,
speed.
eh?
So here's typing on a keyboard, what I typed,
Yeah,
and then
I
what
might try
keytap
and-
3 was able to recover. This is after going through the setup, after going through GNU Radio, then isotope RX with a lot of cleanup. Again, I needed to collect at least 3 kilohertz of sound, and also just an example of what the sound actually sounds like. This was playing music inside of a room and then reflecting off the window. And we can hear a little bit of that sound. And that is the project. The challenges, I mean, this was really interesting. How you
Okay, we only have
this whole thing was
time
really
for
a
one question. I'm sorry.
signal processing. And the improvements to the laser microphone, the biggest thing to the laser microphone was really getting outside of the sound domain, getting into the radio domain. Once you get into there, then you have a lot more processing capabilities, and you have all the sound, a ton of noise that was there.
Closer to the microphone.
And there are plenty of improvements we can make, we can discuss later, but thank you so much. I appreciate your time.
Guys. Okay, so the question is around cyber liability. Do you think it's going to be hard to do because of all the laws around liability?
From